August 19, 1943, Munda Airfield, New Georgia Island. A Marine corporal named Eddie Vasquez crouches in the captured Japanese command post, sorting through scattered equipment while artillery rumbles in the distance. Most of it is junk: shredded maps, broken typewriters, a field telephone with its wires cut. Then he finds something that stops him cold: a radio, Japanese Type 94 Mark VI. He's seen the American version, the SCR-300, strapped to the backs of his fellow Marines 100 times. This thing looks like its grandfather built it in a shed. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The casing is leather and metal, barely larger than a lunchbox. Inside, a single vacuum tube. 1. The Americans are using 18. There's no battery compartment because there are no batteries. Next to the radio sits a wooden box with a hand crank protruding from one side. You want to send a message? Start cranking, keep cranking, stop cranking, and the radio dies. Vasquez picks up the technical manual, can't read a word of Japanese, but the diagrams tell him everything. Maximum range in perfect conditions, 1 kilometer, 6/10 of a mile. The SCR-300 on his buddy's back 300 yards away can reach 3 miles on a bad day, 5 to 8 if you're lucky, and you just flip a switch. No cranking required. He doesn't know it yet, but what he's holding represents one of the most devastating technological gaps in the Pacific War. While American infantry companies coordinate attacks across miles of jungle using portable FM radios that sound like telephone calls, Japanese soldiers are either screaming themselves hoarse or sending runners through machine gun fire because their radios are essentially useless for frontline combat. This isn't just about better engineering, it's about a fundamental difference in how two nations approach the problem of making soldiers talk to each other when bullets are flying. And the price Japan paid for falling behind wasn't measured in dollars. It was measured in battles lost because companies couldn't coordinate, in artillery that arrived too late, in reinforcements that never came because the call for help died when someone's arm got too tired to crank. January 1940, Chicago. The offices of Galvin Manufacturing Corporation, a company that will rename itself Motorola in 7 years, occupy a modest brick building on Augusta Boulevard. Daniel E. Noble, 34 years old, MIT trained, radio engineer, walks into his first day of work carrying a leather briefcase and enough nervous energy to power the building. He's been hired to solve a problem that doesn't have a solution yet. The U.S. Army Signal Corps wants a portable radio for infantry units, not a vehicle radio, not a pack radio that requires 3 men to carry. A radio one man can wear on his back and still have his hands free to fire a rifle. The specifications sound simple until you actually try to build the thing. Voice communication, not just Morse code. 3-mile range minimum. Weatherproof enough to survive jungle humidity and Arctic cold. Tough enough that a soldier can hit the dirt when mortars start falling without turning 35 pounds of electronics into expensive shrapnel. Oh, and it needs to work when you need it to work, which is to say when people are shooting at you. Previous attempts at portable military radios have produced equipment that is technically portable in the sense that a piano is portable if you have enough people willing to hurt their backs. The SCR-194 and SCR-195 backpack radios are £50 each, tune like finicky old car radios, and have reliability issues that make Signal Corps officers write angry memos. The SCR-511, nicknamed the pogo stick for its long staff antenna bisecting a coffee can-sized transceiver, is designed for cavalry. Horse cavalry, in 1940. It's obsolete before it leaves the factory. Galvin Manufacturing has one advantage. They've been building FM mobile radios for police cars since the mid-30s. FM. Frequency modulation. Edwin Armstrong's revolutionary broadcasting method that the commercial radio industry has largely ignored because AM works fine and changing is expensive and complicated. But FM has properties that matter desperately to the military. It resists interference from electrical sources. Vehicle engines, generator motors, The electrical noise that turns AM radio into static soup at exactly the wrong moment. FM just keeps working. The voice quality is clearer, almost like a telephone call instead of a scratchy transmission through a tin can. And here's the critical advantage nobody fully appreciates yet. FM receivers can use something called a squelch circuit. On an AM radio, when nobody's transmitting, you hear a noise. Loud, annoying, constant noise. A radio operator either leaves the volume down and misses calls, or leaves it up and goes slowly insane listening to the roar of empty frequency space. FM squelch silences the radio when there's no transmission. Complete silence. Then someone keys their mic and the voice comes through clear. This sounds like a convenience feature. In combat, it's the difference between a radio operator who can actually function after 6 hours and one whose hearing is damaged and attention span is shredded. Noble assembles his team through winter 1940 and spring 1941. Henryk Magnuski, a Polish émigré and brilliant RF engineer, becomes the principal radio frequency designer. Marion Bond, Lloyd Morris, Bill Vogel. These men have never built anything like what the Signal Corps is demanding. Nobody has. They're going to have to invent it. The first challenge is power. Vacuum tubes, the heart of any 1940s radio, require two kinds of electrical current. Filament voltage to heat the cathodes, typically 1.5 to 6 volts DC. Plate voltage to make the tubes actually amplify signals, anywhere from 45 to 300 volts DC. Portable radios in 1940 used two separate battery packs, A batteries for filaments, B batteries for plates. The weight adds up fast. An 18-tube radio, like the one they're designing, needs serious electrical capacity. The BA-70 battery pack they eventually settle on weighs 13 pounds and provides power for 20 to 30 hours of operation. You can swap to the smaller BA-80 if weight is critical, but you only get 10 to 12 hours. Either way, add the battery to the transceiver unit, throw in the case and accessories, and you're at 32 to 38 pounds, depending on configuration. That's heavier than anyone wants. It's lighter than any alternative that actually works. Tube selection becomes an obsessive hunt for efficiency. They need 18 tubes total to build a proper FM transceiver, with the range and reliability the Army demands. Transmitter section, receiver section, frequency control circuits, modulation stages, power supplies. Each tube has to be chosen not just for performance, but for how much current it draws, how much heat it generates, how likely it is to survive being drop-kicked across a battlefield. The receive operates as a double super heterodyne circuit, which is engineering speak for a receiver design that converts incoming signals through two intermediate frequencies before detection. This makes it more selective, better at rejecting adjacent channel interference, more stable. It's also more complex, more tubes, more ways for things to break. They do it anyway because the alternative is a radio that works fine on a test bench and fails in the field when someone 3 miles away is trying to call in artillery support. Frequency coverage presents another headache. The Signal Corps specifies 40 to 48 MHz, the VHF band. This is higher frequency than most military radios in 1940. Higher frequency means better line of sight range and smaller antennas, but it also means designing circuits that behave properly at frequencies where component tolerances matter and stray capacitance can ruin your whole day. The crystal oscillator problem nearly kills the project before it starts. Most military radios in 1940 use quartz crystals to control frequency, 1 crystal per frequency. Want to operate on 10 different frequencies? Carry 10 crystals, each one individually ground and expensive. The Signal Corps tells Noble's team they can use 2 crystals maximum. 2. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Mass production of crystals hasn't ramped up yet. The military needs millions of crystals for all their radio equipment. Crystal manufacturing is a bottleneck. So figure it out. Magnuski's solution is elegant and insane in equal measure. He designs a tuning system where a single, calibrated dial sets both transmit and receive frequency across 40 channels spanning 8 MHz. The two crystals are used for calibration only. You tune the radio against the crystal-generated frequencies to make sure your dial is accurate, then you lock the tuning and operate anywhere in the band. The mechanical precision required to make this work is absurd. The tuning mechanism has to maintain frequency stability, while a soldier is running, sweating, falling down, and generally abusing the equipment. They build detents into the tuning dial, 40 positions with mechanical stops, so operators can quickly select specific channels without staring at frequency counters. Spring 1942, Fort Knox, Kentucky. The SCR-300 prototypes arrive for final acceptance testing. These tests are not gentle. Signal Corps. Evaluators treat the radios like they're trying to kill them because they are trying to kill them. Soldiers don't baby equipment. If it can't survive rough handling, it won't survive combat. They drop the radios from shoulder height repeatedly. They submerge them in water to test the supposedly weatherproof seals. They operate them in environmental chambers that simulate jungle heat and Arctic cold. They run them continuously at full power until the batteries die, then swap batteries and do it again. The critical test is range. Two evaluators take prototype SCR-300s and walk away from each other across the Fort Knox training areas. Flat terrain, rolling hills, through woods, they measure actual communication distance under field conditions. The specification called for 3 miles. Magnuski and Noble put themselves through a field test before the army even showed up. They stood 8 miles apart, Magnuski on the flat roof of the Tropic Air Building next to the Augusta Boulevard plant, Noble in the Thatcher Woods Forest Preserve parking lot to the west. 8 miles, more than twice the spec. When Noble heard Magnuski's Polish-accented voice crackling through the speaker, loud and clear, he knew they had it. The army tests confirm it. 3 miles is the minimum. 5 to 8 miles is typical, depending on terrain and antenna configuration. Voice quality impresses the evaluators even more than range. FM transmission sounds natural, almost like a telephone call. No distortion, no fading in and out, no static crashes when someone starts a Jeep nearby. The squelch circuit works flawlessly, silencing the receiver between transmissions, letting operators monitor their frequency without going deaf from noise. Ruggedness passes every test. The radio survives drops, water exposure, temperature extremes. The metal case and weather-sealed controls protect the electronics. The vacuum tubes, mounted in shock-absorbing sockets, don't shatter when the unit hits the ground hard. June 1942. The Army Signal Corps awards Galvin Manufacturing a production contract. Build as many as you can, as fast as you can. War is coming, probably faster than anyone wants to admit, and the Army needs thousands of these radios yesterday. Production startup is chaos. Galvin Manufacturing's entire operation has to scale from prototype to mass production. They need suppliers for hundreds of components. Vacuum tubes, capacitors, resistors, transformers, antenna sections, cases, batteries. Every component has to meet military specifications, which are stricter than commercial standards. Everything has to be tested. Everything has to be documented. The factory floor becomes an assembly line where workers build the same sub-assembly over and over until they can do it blindfolded. Radio chassis assembly, wiring harness installation, tube socket mounting, final testing. Quality control inspectors check every 10th unit in detail, pulling radios off the line for electrical testing, mechanical testing, environmental testing. Failures get traced back to the component level. Was it a bad tube, a cold solder joint, a misaligned tuning mechanism? Fix the problem, adjust the process, keep building. Antifungal treatment becomes critical for radios destined for the Pacific Theater. The heat and humidity of jungle environments turn electronics into petri dishes. Fungus grows on anything organic, including the insulation on wires and the phenolic material of circuit boards. Left untreated, a radio will degrade in weeks. Technicians apply specialized varnish over assembled circuit boards, coating everything in a moisture-resistant, antifungal layer. They use rubber grommets to seal case sections, preventing moisture intrusion that would corrode contacts and short circuits. It's painstaking work. It adds time to every build. It's also non-negotiable if you want radios that still work 3 months into a jungle campaign. By December 1943, Motorola is producing approximately 1,000 SCR-300 units per month. By mid-1944, that number climbs to 1,500 per month. Other manufacturers get contracts to build compatible units under different designations. Total production runs to nearly 50,000 units before war's end, August 1943. The SCR-300 sees its first combat action during the New Georgia campaign in the Solomon Islands. Marine infantry companies attacking Munda airfield carry the new radios into battle for the first time. The feedback is immediate and overwhelmingly positive. Company commanders can coordinate with battalion headquarters 3 miles to the rear without wire lines that get cut by artillery. Platoon leaders can call for fire support and actually have the artillery land where it's needed instead of where someone guessed 5 minutes ago. Forward observers, the guys who sit in exposed positions watching enemy movement and calling in strikes, suddenly have reliable communications that work when they need it. Previously, they'd been using SCR-536 handy-talkies, handheld AM, radios with maybe a quarter-mile range on a good day. Trying to adjust artillery fire with a radio that cuts out every 50 yards is like trying to perform surgery with boxing gloves. The SCR-300 changes everything. The radio's range means forward observers can operate from concealed positions well back from the front line and still maintain contact. The voice clarity means fire mission corrections don't get garbled. Left 50, down 25, doesn't become right 55, drop 15 because of static. Shells land where they're supposed to. Fewer American casualties. More effective fire on enemy positions. Colonel Ankenbrandt, after the Munda operation, writes in his after-action report, "They are exactly what is needed for frontline communications in this theatre. The only complaint anyone has is battery life. In continuous operation, the BA-70 battery packs last about a day. In jungle combat, where supply lines are tenuous and resupply is irregular, dead, batteries become a significant problem. Units start requesting double and triple the normal battery allocation. Supply officers grumble, but they comply because radios that work are too valuable to let die for want of batteries." Tokyo, 1940. The Imperial Japanese Army's Signal Corps faces similar challenges to the Americans. Infantry units need portable radios for coordination and fire support. The solutions they develop are remarkably different. The Type 94 series radios, first designed in 1934, hence the designation based on the Japanese Imperial Year 2694, represent Japanese thinking on portable military communications. The Type 94 Mark VI, the most common infantry-level radio, is built around fundamentally different assumptions than the SCR-300. It's a single-tube transceiver operating in the 23 to 31 MHz range. Single tube, the entire transmitter and receiver function, share one vacuum tube, a Type 31MC. This makes it compact and light, about 5 pounds without the hand crank generator. It also makes it weak. Transmitter output is half a watt, 0.5 watts. The SCR-300 pumps out 5 watts from its final amplifier stage, 10 times more power. Range for the Type 94 Mark VI under ideal conditions is 1 kilometer, 0.6 of a mile. In jungle terrain with any interference, that drops to maybe half a kilometer. The SCR-300's 3-mile range is literally 15 times better. But the real difference isn't in the specs. It's in how the radios actually work in combat. The SCR-300 is battery-powered. You strap it on, you flip switches, you talk. The Type 94 Mark VI requires a hand crank generator to provide power for transmitting. The generator, a separate wooden box with a handle, produces the high voltage needed for the tube's plate circuit. Want to send a message? Someone starts. Cranking. Steady cranking. The radio operator speaks into the throat microphone while his assistant cranks. Stop cranking and the transmission dies mid-word. Try doing this while under fire. Try doing this after you've been awake for 30 hours. Try doing this when your unit is moving and every man is already carrying 60 pounds of equipment and nobody wants generator cranking duty because your arm feels like it's going to fall off after 5 minutes. The Type 94 Mark V radio, used at company and battalion level, is slightly better. It can use dry cell batteries for receiving, so at least you can listen without cranking. But transmitting still requires the hand generator, and it's still CW only. Morse code. No voice. You want to send a message? You tap it out in code while someone cranks. The receiving operator copies the Morse, decodes it, delivers the message. This works fine when trained telegraph operators have time to carefully send and receive. It's nearly useless for the kind of fluid, rapid coordination American infantry companies are doing with voice radios. The Type 94 Mark III series, used at division and regiment level, represents the higher end of Japanese field communications. It's actually a fairly sophisticated design for 1934. A separate transmitter and receiver, both using vacuum tubes, with interchangeable plug-in coils for different frequency ranges. The transmitter outputs 10 to 15 watts on CW. Range under good conditions can reach 80 kilometers, about 50 miles, but it requires transport by mule or multiple men. 3 wooden cases hold the transmitter, receiver, batteries, generator, and accessories. The generator is hand-crank powered. Calling this portable is like calling a machine gun portable, because technically a crew of 3 can move it, and it's still CW only, no voice capability. Japanese military radio design philosophy in the 1930s prioritized simplicity and fourther, ease of manufacture, single-tube designs, regenerative receivers, crystal-controlled transmitters using plug-in coils. These radios are actually quite clever from an engineering standpoint. They accomplish a lot with minimal components. They're relatively easy to build with Japan's industrial capacity, which in 1940 is substantial but not unlimited. But they're a generation behind where American and British designs are headed. The Japanese military largely missed the FM revolution that American engineers embraced. Their radios are AM, amplitude modulation, the same technology civilian broadcast stations use. AM works fine in ideal conditions. It falls apart in the electrical noise environment of modern mechanized warfare. Tanks, trucks, generators, electrical equipment of all kinds produce radio frequency interference that turns AM communication into garbage. FM resists this interference. The Japanese also missed the critical importance of voice communication for frontline units. The Type 94 series radios are mostly CW telegraph. This made sense in 1934, when vacuum tube voice transmitters were expensive and complex. By 1940, when the Americans are building 18-tube FM transceivers with voice clarity that rivals telephone connections, CW-only radios are obsolete for infantry use. There's another factor that cripples Japanese radio effectiveness: training. Operating a Type 94 radio requires skill, Morse code proficiency, frequency selection using plug-in coils, tuning both transmitter and receiver for resonance. The SCR-300 is, by comparison, idiot-proof. 40 channel positions clearly marked. Turn it to channel 15. The guy you're calling is on channel 15. You talk. Training time for SCR-300 operation is measured in hours, not weeks. The Americans understand something the Japanese don't fully appreciate until it's too late. Frontline infantry communication doesn't need sophisticated operators. It needs communication that works when 19-year-old privates who barely graduated high school are cold, scared, and haven't slept in 40 hours. It needs radios simple enough that anyone can use them and rugged enough that they keep working after being dropped in mud. Japanese manufacturing capacity also constrains their radio development. Vacuum tubes require precision glasswork and specialized materials. Japan produces quality vacuum tubes, but not in the quantities American factories are churning out. The United States is producing tubes by the millions for civilian radios, military radios, radar sets, electronic warfare equipment. Economics of scale drive costs down and quality up. Japan can't match this production volume, so they design around scarcity. Single-tube radios, minimal tube counts in everything, hand-crank generators, instead of battery packs that require thousands of batteries. It's logical given their constraints. It's also catastrophically limiting when they end up fighting an opponent who doesn't have those constraints. February 1944, Guadalcanal Island. The Japanese have been gone for over a year, but their debris field remains. Abandoned equipment, shattered bunkers, mass graves hastily covered. A technical intelligence team from the U.S. Army Signal Corps, designated Task Force 6-8-3, spends 3 weeks cataloguing captured Japanese radio equipment for analysis. Lieutenant Colonel Raymond Foster leads the team. He's a career signals officer, peacetime engineer from Bell Labs, recalled to active duty in 1942 specifically because he understands radio technology at a level most Army officers don't. He's examined German radio equipment captured in North Africa. He knows what good military communications look like. The Japanese equipment surprises him, but not in the way he expected. The Type 94 Mark III transceiver, sitting on his examination table, is beautifully constructed. The component layout is logical, the mechanical design clever. Plug-in coils for frequency changes, efficient use of space, quality construction throughout. This isn't crude equipment. Japanese engineers knew what they were doing, but when Foster compares specifications against American equivalents, the numbers tell a brutal story. The Mark III transmitter outputs 15 watts maximum. The American SCR-300 vehicular radio outputs 40 watts. The Mark III receiver is a super heterodyne design, which is good, but it's a single conversion design, and the selectivity is poor compared to American double conversion receivers. Range calculations are even more damning. The Mark III claims 80-kilometer range, 50 miles, in ideal conditions. Flat terrain, perfect weather, optimal antenna setup. The SCR-300, designed for handheld portable use, not vehicle mounting, reliably communicates across 3 to 5 miles of jungle terrain with a simple whip antenna. The Japanese division-level radio, requiring mules to transport, barely outperforms the American infantry backpack radio in actual field conditions. Foster writes in his technical report, dated March 8, 1944. Japanese radio materiel shows evidence of sound engineering principles applied with resource constraints. Designs are several years behind current American and British standards. Notable deficiencies include lack of frequency modulation adoption, reliance on amplitude modulation susceptible to interference, minimal use of squelch circuits, dependence on hand-crank generators for portable equipment power, absence of voice capability in most field sets. The report continues for 38 pages, cataloguing every captured radio type, every specification, every comparative analysis against US equipment. The most damning section addresses the Type 94 Mark VI infantry radio. Foster's team field tests captured units. They set up 2 Mark VI radios and attempt communication at various ranges. At 500 meters, half a kilometer, communication is possible but requires optimal conditions. No terrain interference, antennas fully extended, someone cranking steadily. At 1 kilometer, the specified maximum range, communication becomes intermittent. Any terrain feature between the radios, any electrical interference, breaks the signal. Compare this to the SCR-300 field test data. Reliable communication at 3 miles becomes standard. 5 miles is routine. 8 miles happens regularly in favorable conditions. Foster's team interviews captured Japanese communications personnel. The interviews, conducted through interpreters, reveal frustration that American intelligence finds both surprising and informative. A Japanese Signal Corps corporal, captured on Bougainville, describes his experience with the Type 94 Mark VI. Through the interpreter, the hand generator is the biggest problem. In combat, you need both hands for the radio. The sender speaks, the assistant cranks. If you are alone, you cannot transmit. If you are under fire, cranking makes you a target because you cannot move. The range is insufficient. Many times we cannot reach battalion headquarters. We send runners instead. Another prisoner, a communications specialist from a Japanese Army regiment on New Georgia, provides technical perspective. We knew American radios were better. We captured SCR-300 handheld radios on Guadalcanal. Even their small handheld radio has longer range than our Type 94 Mark VI. The American equipment is heavy, but it works without generators. This is a significant advantage. The key phrase jumps out. We knew American radios were better. This isn't intelligence failure. Japanese forces understood their communications inferiority. They examined captured American equipment. They saw the technology gap. June 1944, Tokyo. The Naval Technical Research Institute receives 3 captured American radios for analysis. An SCR-300 recovered from a destroyed American position on Saipan. An SCR-536 handy-talkie found in a wrecked landing craft. An SCR-508 vehicular radio from a burned-out Sherman tank. The examination team is led by Commander Nakamura Takeshi, a naval officer with an electrical engineering degree from Tokyo Imperial University. He spent 2 years in the United States before the war, studying at MIT as part of a naval exchange program. He knows American engineering capability. He's not optimistic about what they'll find. The SCR-300 disassembly takes 3 days. Nakamura's team photographs every component, measures every voltage, traces every circuit. The report they generate is technically detailed and brutally honest. The use of frequency modulation represents a fundamental advantage the Japanese military has not adopted. The 18-tube design allows for sophisticated unitos, circuits that improve selectivity, sensitivity, and stability beyond what Japanese portable radios achieve. The battery capacity required to power such equipment represents a logistics advantage Japan cannot match with current industrial capacity. The squelch circuit receives particular attention. Japanese radios don't have this feature. Nakamura notes in his report, the automatic noise suppression circuit eliminates operator fatigue from continuous monitoring. This is a significant tactical advantage over our current equipment, which requires constant audio monitoring. He's describing squelch without using the American term, but he understands exactly what it does and why it matters. The frequency coverage specification surprises the Japanese engineers. 40 to 48 MHz, the VHF band. Most Japanese military radios operate in the HF band, high frequency, 3 to 30 MHz. VHF offers advantages in line-of-sight communication and antenna efficiency that the Japanese have not exploited systematically. The channel selection system, 40 discrete channels set by a single dial with mechanical detents, represents operational sophistication Japanese radios lack. Most Type 94 series radios require manual tuning by the operator, adjusting transmitter and receiver separately to establish communication. The American system is faster and requires less training. Nakamura's report includes a section on comparative range calculations. Using the captured SCR-300 specifications and confirmed field reports from Japanese forces who encountered American units, he calculates actual operational range under combat conditions. The Americans routinely communicate across distances that would require Japanese forces to use division-level equipment transported by vehicle. The tactical implications are profound, and Nakamura doesn't shy from stating them clearly. American infantry companies possess communications capability equivalent to Japanese regimental headquarters elements. This disparity creates coordination advantages at every echelon. American forces can concentrate artillery support rapidly, adjust fire in real time, and coordinate maneuver elements across dispersed positions. Japanese forces operating with Type 94 Mark VI radios at company level cannot match this capability. The report goes to the Naval General Staff. It goes to the Army General Staff. It goes to the Ministry of Munitions. The response is essentially, we know. They know. Everyone knows. The question isn't whether American communications technology is superior. The question is what Japan can do about it with limited industrial capacity, material shortages, and a war they're already losing. The answer is, not much. Not fast enough. Japanese engineers attempt to develop improved radio equipment through 1944 and 45. The Type 3 Mark I airborne radio, introduced late in 43, shows marked improvement over earlier designs. It uses more modern components, has better frequency stability, includes some features borrowed from captured American equipment, but it's for aircraft, not infantry. Ground forces continue using Type 94 series equipment because there's no production capacity to develop and manufacture replacements. The factories that could build improved radios are building radar sets, aircraft radios, shipboard communications equipment. Everything is prioritized for the Navy and Air Force. Infantry communications get whatever is left, which is equipment designed in the 30s and barely improved since. December 1944. Leyte Island, Philippines. The U.S. Army's 6th Infantry Division attacks Japanese positions in the Ormoc Valley. American companies advance in coordinated bounds, each company commander carrying an SCR-300, maintaining continuous contact with battalion headquarters. Artillery forward observers, positioned on high ground with Perthines of the Perthers, a clear line of sight to Japanese defensive positions, call fire missions directly to artillery batteries 4 miles to the rear. The artillery response time, from target identification to shells impacting, averages 4 minutes. Japanese forces defending the same positions use runners for most communications. Radio equipment is present at battalion and regiment level, but company commanders have no reliable means to coordinate with higher headquarters beyond sending men back through artillery fire and American patrols. When Japanese forces attempt to counterattack, coordination breaks down immediately. Companies attack piecemeal because there's no way to synchronize movement. Artillery support, when it comes, is pre-planned because there's no forward observer capability to adjust fire dynamically. American after-action reports note the disjointed nature of Japanese attacks. Companies emerge from jungle cover at different times, allowing American forces to defeat them sequentially, rather than facing coordinated assaults. Intelligence officers initially attribute this to poor Japanese tactics. Eventually, they realize it's not poor tactics. It's the inevitable result of communication systems that don't work in mobile combat. You can plan coordinated attacks beautifully on maps in headquarters. Executing them requires communication. Without working radios, execution becomes wishful thinking. The Battle of Leyte produces thousands of pages of American signals intelligence reports. Intercept stations record Japanese radio traffic, analyze frequencies, catalog call signs, identify units. What's notable is how sparse the Japanese tactical radio traffic is compared to American nets. American infantry battalions generate continuous radio traffic. Fire missions, movement reports, situation updates, coordination messages. The radio spectrum is alive with communication. Japanese radio traffic at tactical level is minimal. Long periods of silence punctuated by brief transmissions, mostly in Morse code, often incomplete or cut short. The Japanese aren't maintaining radio silence as a tactical measure. They're simply not using radios because the radios don't work well enough to justify the effort. February 1945. Iwo Jima. Marine companies assault fortified Japanese positions using tactics refined through 3 years of island fighting. Every rifle company has multiple SCR-300s. Every platoon leader carries an SCR-536 handheld. Company commanders can talk to any platoon instantly. Battalion commanders coordinate 3 companies simultaneously, using radio nets that function reliably despite volcanic ash, smoke, and the electromagnetic chaos of thousands of weapons firing. Japanese defenders, dug into elaborate tunnel systems, have wired field telephones connecting defensive positions. The wires get cut by American artillery. Marines advancing through the defenses destroy telephone lines systematically. Japanese. Communications collapse to runners and hand signals. Colonel Kanehiko Atsushi, commanding Japanese forces in the northern sector, writes in his diary on February 21st, "Communication with subordinate units has become impossible. Telephone lines cut by bombardment, radio equipment destroyed or unable to function in current conditions. I do not know the situation of forces defending the western beaches. Send runners, but they do not return. Assume all positions under heavy attack, but cannot coordinate response." Atsushi will die 6 days later when Marines overrun his command post. His diary, recovered and translated, becomes part of the intelligence archive that tells the story of how communication failure multiplies combat ineffectiveness. The technological disparity isn't subtle. It's not a matter of slight advantages accruing over time. It's a chasm. American infantry operates with communications technology that allows coordination across miles of terrain in real time. Japanese infantry operates with technology that barely works across half a kilometer under ideal conditions and requires hand-cranking a generator while someone shoots at you. This isn't just about radios. It's about how modern warfare works. Maneuver warfare, combined arms coordination, responsive artillery support, all of it depends on communication. Without working communications, a military force reverts to Napoleonic tactics. Send orders, hope they arrive, hope units execute as planned. No adaptation, no flexibility, no real-time coordination. The Marines on Iwo Jima can adjust tactics minute by minute because company commanders talk to each other. Company Fox is pinned down. We're shifting left to support. Battalion be ready to shift artillery. That conversation happens in real time, and the entire battalion adjusts accordingly. The Japanese on Iwo Jima cannot do this. Defensive plans are solid, positions are well fortified, soldiers are brave and determined. But once fighting starts and communication breaks down, the defense fragments into isolated strong points that Marines reduce one by one. March 1945. A U.S. Naval Technical Intelligence report, compiled from captured Japanese documents and prisoner interrogations, includes a section on enemy communications equipment assessment. The report quotes from a Japanese Army technical manual captured on Luzon. The manual, dated 1944, includes a section comparing Japanese and American radio equipment. The comparison is startling not because it reveals anything American intelligence didn't already know, but because it confirms Japanese military leadership fully understood their communications inferiority and could do nothing about it. The translated text reads, "American portable radio equipment demonstrates significant advantages in range, reliability, and ease of operation. The SCR-300 model achieves communication distances exceeding 5 kilometers under field conditions, more than 5 times the effective range of Type 94 equipment. American equipment operates using battery power without requiring hand-cranked generators, providing operational advantages in mobile combat situations. Japanese equipment performs adequately when communication can be established under controlled conditions, but American equipment maintains reliable communication under combat conditions where Japanese equipment fails." That last line is the key. Japanese equipment performs adequately when communication can be established under controlled conditions. In other words, it works fine on the parade ground. In combat, when it matters, it fails. The technical manual continues with recommendations for operators using Type 94 equipment in combat. Establish communication before moving to engagement areas. Designate generator operators to ensure continuous power during transmission. Position radios in protected locations where generator operators will not be exposed to enemy fire. Maintain redundant communication methods, including runners and field telephones. These recommendations read like instructions for making obsolete equipment slightly less useless. They're trying to solve tactical problems caused by technical inadequacy. The final section of the captured manual addresses what Japanese forces should do when encountering American radio equipment. Captured American radio equipment should be immediately reported to higher headquarters for technical intelligence exploitation. Do not attempt to operate captured equipment without proper training, as American systems use different frequency ranges and modulation methods. Priority should be given to recovering SCR series portable radio equipment for technical analysis. They want captured American radios specifically because they know those radios are better than anything Japan has. April 1945. Okinawa. The last major battle of the Pacific War becomes the ultimate test of every tactical system both sides have developed. American forces employ radio communications refined through 3 years of combat. Every level of command, from division down to squad, has reliable radio capability. Coordination is seamless. Artillery support is devastating because forward observers can adjust fire in real time. Air support arrives quickly because ground controllers talk directly to pilots. Japanese forces defend using tactics that minimize their communication disadvantages. Static defense from prepared positions, pre-planned artillery fires, limited maneuver. It's not because Japanese commanders lack imagination. It's because their communications equipment can't support the kind of fluid, coordinated operations American forces execute routinely. The battle lasts 82 days. American forces suffer over 60,000 casualties, including 12,000 killed. Japanese forces suffer over 100,000 dead. The casualty ratio reflects many factors: American firepower superiority, air dominance, naval gunfire support. But communication plays a crucial role. American forces adapt constantly. When tactics fail, they shift approaches immediately. Japanese forces, unable to coordinate across their defensive zones, fight effectively in local engagements, but fail to mount coordinated counterattacks that might disrupt American operations. Intelligence officers examining captured Japanese command posts on Okinawa find extensive telephone wire but minimal radio equipment. The wire systems are elaborate, connecting defensive positions through underground cables. They work until American artillery cuts them, which happens early and often. Backup radio systems exist, but they're insufficient. A Japanese battalion might have one Type 94 Mark III radio, for coordinating 600 men across a defensive zone. American battalions have dozens of radios, different types for different purposes, but all of them working, all of them, allowing real-time coordination that Japanese forces simply cannot match. August 1945. The war ends before Japanese industry can close the communications technology gap. Plans exist for improved radio equipment, designs incorporating lessons learned from captured American gear. But the factories that would build these radios are bombed, the material supplies are cut off, and the war ends with Japanese infantry still carrying Type 94 radios fundamentally unchanged from the 1934 design. Post-war analysis by the U.S. Strategic Bombing Survey includes extensive examination of Japanese military communications. The survey team interviews Japanese officers, examines production records, analyzes tactical doctrine. The conclusion is unanimous. Japanese communications inferiority contributed significantly to tactical defeats across the Pacific. Not because Japanese soldiers fought poorly, they fought with determination and skill. But modern warfare is a systems competition. The side with better systems, integrated effectively, wins. The systems include weapons, logistics, intelligence, and, critically, communications. Japan entered World War II with communication systems adequate for the previous war. Radios that worked when armies moved slowly, when coordination happened through written orders delivered by messenger, when battles developed over days and weeks. The Americans fought with communications systems designed for the war they were actually fighting, radios that enabled rapid coordination, flexible tactics, overwhelming firepower concentrated exactly where needed. The gap was unbridgeable, not because Japanese engineers lacked ability, but because you can't redesign and mass-produce an entirely new communications infrastructure during a war you're losing. The SCR-300, designed in Chicago starting in 1940, deployed to combat in 1943, shaped Pacific War tactics as profoundly as any weapon system. Not because it killed enemies directly, but because it multiplied the effectiveness of everything else. Artillery arrived faster. Maneuver happened more smoothly. Adaptation occurred continuously. The Marine Corporal on Munda in 1943, comparing the SCR-300 on his buddy's back to the captured Japanese radio with its hand crank, saw the physical embodiment of technological disparity. Heavy versus light, 18 tubes versus 1, batteries versus hand cranks, 3 miles versus half a mile. But the real disparity was deeper. It was the difference between communications technology that enabled modern combined arms warfare and communications technology that constrained forces to tactics from an earlier era. The difference between systems designed with unlimited resources and systems designed under scarcity. The difference between engineering that prioritized operator convenience and engineering that prioritized minimal component count. Sense in context. Japanese engineers made rational decisions given their constraints. American engineers made different decisions given different constraints. The results were systems that looked similar, both called portable military radios, but functioned in completely different universes of capability. And in war, capability gaps don't accumulate slowly. They compound exponentially until tactical advantages become operational, advantages become strategic advantages, become campaigns lost, and battles that never should have been fought. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.